welcome back to another video. Today, as per the request of many of my friends and some of you guys, I will be going back to U-Substitution, and we're going to be going over some examples today. Hopefully this will get you a better understanding of how to do it yourself and how to apply it to new problems that you haven't seen before. So let's get into it. For this video, I have prepared 8 integrals that maybe not require U-Substitution, but they'll be great for understanding the principles behind it and when to use it, what to look for, all of that. 4 of them will be indefinite integrals and 4 of them will be definite integrals, so we will have to worry about reparametrization for those integrals. But let's get started with the first one. The first integral on the list is going to be the indefinite integral of 2x times cosine of x squared. Now, if this integral were just cosine of x squared, we would not actually be able to find an elementary solution of it. However, because there's that 2x in front, we can perform a U-substitution. To do so, we'll need to choose what our u is going to be. We have an x squared and we have a 2x. The pattern that we're always looking for in a U-substitution is to find a function and the derivative of that function that's being multiplied by the dx. For example, this x squared isn't actually being multiplied by dx because it's being cosigned first, right? But this 2x is directly applied to the dx. So if we can look for something that will give us a derivative, which is 2x, then we'd be able to use substitution. Now, the great thing about this integral is that that's right here. X squared is the integral of 2x. So we can set u equal to x squared. And now, just as a reminder, the reason why we're able to do this is because we reparametrize by doing this. Du dx is equal to 2x. If we had said that u equals x squared and plugged it in right here and kept it in dx, then it would all be for naught because we're no longer integrating with respect to u because we have the dx there. I went over this idea in my dedicated video on the U-substitution as an idea, so go check that out if you're confused as to why we're doing this. This video is just for practice problems, so the conceptual stuff is in there, so check it out. Now, the next step here is to multiply this dx on both sides so that we get du equals 2x dx. Now we have 2x times dx right here, so we can substitute du straight in there for that. Doing so nets us this new integral. We know that x squared is u, so we plug in u inside of that cosine, and this 2x dx is the same as du. Now this integral becomes the integral of cosine u with respect to u. Now this one, we should know by now, is just going to be sine u, and of course plus c, or you can put it back into the x world. We know u equals x squared, so we'll use that as our translation tool. Sine doesn't change, and then this inside u is going to be x squared, and then of course still plus c at the end. And this is the final solution for our original integral. Moving on to our second integral, this one's going to be a definite integral, so we'll have to worry about the parameters when we perform our U-sub. It's going to be the integral from pi over 2 to 3 pi over 2 of sine x times cosine x, of course, dx. Now, if we're looking to U-substitute, we need a function and its derivative. Now, sine and cosine are derivatives of each other, but since the derivative of cosine is negative sine and the derivative of sine is positive cosine, we'll use u equals sine x because then our derivative will still be positive and we won't have to deal with extra negatives for no reason. So we will set u equal to sine x, which means I won't do the du dx part and then multiply. I'm going to skip that step. Hopefully you can figure out how to do that since I just showed you already. But I'm going to write that du is going to be equal to cosine x dx. Cosine x dx, of course, being right there, so we'll know that we can translate that into just du, and then this sine x will be our u. Now, it's not just as simple as plugging all that in. We'll do that first, but we have to change our limits, our bounds of integration. Now, this is from x is pi over 2 to x is 3 pi over 2. For u, well, let's find out. If x is pi over 2, u is equal to sine of pi over 2. That's, of course, going to be positive 1. And then 3 pi over 2, sine of 3 pi over 2 is going to be negative 1. And I'll show that on the unit circle really fast. This is pi over 2. This angle right here, it's 90 degrees. And then 3 pi over 2 is going to be all the way down here. Remember that sine is the y value of this point, so all the way up here is 1, all the way down here is going to be negative 1. Now this creates something interesting. Our integral is now going from positive 1 to negative 1. How can that be? How come our integral is going backwards? Well, a simple trick that we can do to fix this is to put a negative. The negative integral from negative 1 to 1 of u du. Now, why does this work? Well, if you consider the fundamental theorem of calculus, this would go to whatever the antiderivative is. Obviously, we know it's going to be 1/2 u squared, but it doesn't matter what the inside of the function is. We're just talking about the bounds right now. By the fundamental theorem of calculus, we'll have the antiderivative of the inside evaluated at negative 1 minus the antiderivative evaluated at 1. So we have the antiderivative evaluated at negative 1 minus the antiderivative evaluated at 1. If you just apply a negative to this, it'll switch this order. It'll go from 1 to negative 1, which is the same as saying the bounds from negative 1 to 1. Now, with that out of the way, we can finally evaluate. This integral will, of course, be 1/2 u squared, and then it'll be evaluated from negative 1 to 1, and we have this negative in front right here. Now, u squared evaluated at 1 is, of course, just going to be 1, and then times negative 1/2 in the front. So we're going to have negative 1/2 minus u squared evaluated at negative 1. That is, of course, going to be just positive 1 again, times negative 1/2. We're going to get negative 1/2. Now this actually evaluates to 0. We have negative 1/2 minus negative, basically plus 1/2, so 1/2 minus 1/2. And our final answer will be 0. For our third integral, we're going to be doing something a little more interesting. We're actually going to be proving the integral of tangent x. It's going to be the indefinite integral, and we're going to be using U-substitution to figure it out. If you're taking Calculus 1 right now, you may have already seen the integral of tangent x and just been told to memorize it. But here we're actually going to talk about where it comes from by using U-substitution. So let's get into it. The first step is to rewrite tangent x. We know that tangent x is equal to sine over cosine, so we're going to write that right here. Sine x over cosine x dx. Now, remember, when you do a u-sub, you're looking for the derivative of a function that's being multiplied directly by dx. In this case, cosine x is not being multiplied directly by dx because it's in the denominator, but the sine x is. So we'll use our u to be cosine x. And now our du is going to be negative sine x dx. And of course we have sine x dx right here, and we can turn it into negative by doing this. Just putting a negative inside and a negative outside. They'll cancel in the end, but it'll help for our u substitution here. So this is going to be the integral, negative of course. Negative sine x dx is just going to be du, and then we have 1 over cosine, which is 1 over u. So it's going to be 1 over u du. This is, of course, negative ln u plus c, but our u is cosine x. So we really have the negative natural log of cosine x plus c. And then another form, because of the rules of logarithms, you can bring this negative inside as a power. You raise anything to the negative 1, you flip it, so it's the natural log of 1 over cosine. 1 over cosine is secant. So an alternate form is the natural log of secant x plus c. And that will be our final answer. For our fourth integral, we'll be going from 1 to e of the integral natural log of x over x, and of course dx. Now, for this one, it might be a lot trickier to find the correct u substitution. I mean, I was just talking about how you always want to make sure that the derivative of u is the function that's being multiplied directly by dx. If you look for that in here, you you might notice that the natural log of x is being directly multiplied, but not this x. So how are we supposed to get there? If we say u equals x, then our du is not going to be ln x dx. And this requires some out-of-the-box thinking for sure, but we can rewrite this integral as the integral from 1 to e of natural log of x times 1 over x times dx. And now we see a difference. All of a sudden, we have two options for what the derivative of u will be. And we see that we can have a u here and a du dx here. The derivative of natural log of x is 1 over x, and it's being directly multiplied by dx, so it makes a perfect candidate for u substitution. So let's do it. U equals natural log of x, therefore du is equal to 1 over x dx. Now we have our du, and we have our u, and now we can just reparameterize and solve the new integral. So doing all those steps, we'll get the integral of u du, and our new parameters will be, instead of x is 1 to x is e, when x is 1, u will be the natural log of 1, which is 0. So we'll be going from u equals 0 to, when x is e, the natural log of e is of course 1. So u will be equal to 1, and we have the integral from 0 to 1 of u du. This should be pretty easy. We'll evaluate as 1/2 u squared, evaluated from 0 to 1. Don't have to worry about evaluated at 0, because this will go to 0. So evaluated at 1, 1 squared is 1, times 1/2 is 1/2. We'll get 1/2 as our final answer. And that'll be our final solution for this integral. For our next integral, we'll be doing something pretty easy, pretty simple. It will be the integral of tangent x times secant squared x dx. And this will be an indefinite integral. Now, this is a pretty easy pattern to spot as long as you know your trigonometric derivatives. The derivative of tangent x is secant squared x. So let's use that for our u. U equals tangent x. Therefore, du equals secant squared x dx. Okay, so now we know our u and we know our du. So this will become the integral of u du. Now, how do we evaluate this? Well, of course, it's just going to be 1/2 u squared again. 1/2 u squared plus c, but let's put it back into the x world. U is equal to tangent x, so it's going to be 1/2 tangent squared x plus c. And that will be our final answer for this integral. For this next integral, we're going to be doing something pretty similar to this, except instead, we're going to make it tangent squared secant squared. That might make things a little tricky, and let me add a little extra. We're going to add some parameters to it too, and make it a definite integral. It will be going from 0 to pi over 4. Well, how the heck do we do this now? Okay, well, maybe we choose u equals tangent squared x this time. No, that'll still have a tangent x in our... that's no good. Well, we don't have to actually change our u at all from the last question. We can just keep it as u equals tangent x. And then du will equal secant squared x dx. Now we have our du, and tangent squared x, well, we can rewrite this still in terms of just u, because that's just u squared. Now that's an important concept to think about in U-substitution. A lot of the times, you won't actually end up with just a u or just a 1 over u. Sometimes you have to realize that as long as you have one bit that'll get you the derivative you want, as long as the thing that's modifying it, in this case it's being squared, is something that you can still write in terms of u, then you'll be good by the end of it. Now, using these parameters, we'll take the new integral. Now, tangent of 0 is still just going to be 0 for u. Tangent of pi over 4 is, of course, 1. So this will be the integral going from 0 to 1 of u squared du. This is, of course, 1/3 u cubed, evaluated from 0 to 1. And this is just going to be 1/3. And that is our final answer for this integral. for our next integral, this will be the last indefinite integral that we do today. It will be the integral of 1 over x squared e to the 1 over x dx. Now for this one, well, what's being multiplied directly by the dx? We have 1 over x squared and we have e to the 1 over x. Well, e to the 1 over x, that's a little gross, right? But this 1 over x squared, that's pretty nice. How are we going to find something that has the derivative of 1 over x squared? Well, the derivative of 1 over x is negative 1 over x squared, and that's pretty dang close. So we can rewrite this integral in a way that'll give us that negative 1 over x squared. And that's pretty easy. Just put a negative here and a negative here. We did this earlier with one of the other integrals. It's a pretty common trick that you'll see, along with adding constants by multiplying inside the integral and dividing on the outside. Just a good habit to get into to be able to spot these kinds of things. So now what we can do is we can say that u is equal to 1 over x, which means that du will equal negative 1 over x squared dx. So now we have our du, and this will be our u. So we get the negative integral of e to the u du. The integral of e to the u is, of course, still e to the u. So this will be negative e to the u plus c. Of course, we want it back in the x world, so our final answer will be negative e to the 1 over x plus c. And that is the final answer for this integral. Now, for the last integral of this video, we will be doing a definite integral from 0 to 3 of x over 1 plus x squared. Now, if this were 1 over 1 plus x squared, it would actually be a trig substitution in order to solve this integral. But because of this x, we can actually do a U-substitution. Now, you may think to yourself, okay, well, x squared will get us to 2x, so we can maybe do 2 here and a 1/2 here, u equals x squared, and then we're golden. You could do that, or you could say that u is equal to 1 plus x squared. That way, you get the entire denominator covered in u, and this 1 doesn't actually change the value of the derivative of u, because if you add a constant, it doesn't change the value of the derivative. So du will still equal 2x dx. We have 2x dx right here, so that's going to be our du. And then this right here is our u. So 1/2 times the integral. Now we have to reparameterize. When x is 0, u is going to be equal to 1. When x is 3, 3 squared is 9, plus 1 is 10. And then this is the integral of 1 over u du. So the integral of 1 over u is, of course, the natural log of u. So we'll write that here, 1/2 times natural log of u, evaluated from 1 to 10. Now this is pretty easy. It's just going to be 1/2 natural log of 10. Okay, well, what about the 1? Well, natural log of 1 is just going to be 0, because natural log is log base e, and log base anything of 1 is going to be 0. So our final answer is going to be 1/2 natural log of 10. And that is our final answer for the final integral of this video. Thank you guys so much for watching.